Mysterious, unseen masses are drifting through space, objects that we've long questioned but never had answers for, until now. In this video, we're bringing you the latest discoveries about what scientists have just revealed about what lies inside a black hole. This is going to get wild. The journey into the concept of black holes began back in 1916 when Albert Einstein's general theory of relativity first predicted their existence. However, the term black hole wouldn't be coined until nearly 50 years later. While some scientists accepted Einstein's theory, others were skeptical until the discovery of Cygnus X-1 in the late 1960s. During studies of the Cygnus constellation, astronomers observed an unusually bright blue star emitting X-rays. This star wasn't just any ordinary star. It was orbiting a massive, unseen object. Upon further analysis, scientists realized that the X-rays were being pulled toward this mysterious object, and that it was devouring everything in its vicinity. This discovery was the first concrete evidence that black holes existed. What followed Cygnus X-1 was a flurry of discoveries, including the realization that there might be around 100 million black holes in the Milky Way alone. Though these numbers are still uncertain due to the difficulty of detecting black holes, estimates suggest they are in the millions, which makes them all the more important to study. According to most physicists, a black hole is an object where everything that enters it is crushed down to a singularity, a point of infinite density. Simply put, black holes distort space and time to such an extent that anything falling into one would be stretched into a spaghetti-like form, gradually being torn apart as it nears the singularity. One of the scariest aspects of black holes is their unpredictable nature. Even though the closest black hole to Earth is 500 light-years away, it still raises the question: can black holes eventually swallow the Earth? In 2021, scientists captured the first clear image of a black hole, M87, a breakthrough that provided more evidence about how they function. Researchers discovered that black holes are not just one vast nothingness but have three distinct layers. To even reach the center, known as the singularity, you must pass through two event horizons. The first, the outer event horizon, marks the point where nothing can escape the black hole's pull, not even light. Beyond this point, the gravity becomes so intense that nothing can get out unless it travels faster than the speed of light, which, as we know, is impossible. Next comes the inner event horizon, followed by the singularity, where all the mass of the black hole is packed into an incredibly small space. In essence, the singularity is where physics as we know it breaks down, and the laws of the universe cease to apply. To make matters even more terrifying, each black hole behaves differently, meaning that what we learn about one black hole might not apply to others. But how do scientists study such mysterious objects? Unlike stars or planets, black holes cannot be directly observed. Researchers rely on studying the radiation emitted by the gas and dust surrounding them. We can't send a probe into a black hole either, because once it crosses the event horizon, it is lost forever. This leaves scientists with the difficult task of understanding these incredibly powerful cosmic phenomena through indirect means. And while they can capture images of black holes in 2D, they are still unable to explore the singularity itself, as anything approaching it would be crushed into oblivion. However, despite these challenges, scientists have developed several hypotheses about what might lie inside a black hole. One of the most exciting possibilities comes from the movie Interstellar, which suggests that black holes might not just be voids of nothingness. Instead, the area beyond the event horizon could be a gateway to other worlds and even other universes. This would mean that black holes might act as wormholes, offering shortcuts for interstellar travel, an idea that was once thought impossible. On the other end of the spectrum, there are theories that challenge the existence of black holes altogether. Dr. Enrico Raldi, a scientist based in Tokyo, and his team have been working to understand black holes in a different way. They propose a theory of holographic duality, suggesting that black holes might not be real, solid objects at all, but rather multidimensional projections. Raldi and his team have used quantum models to test this hypothesis, and through their research, they've concluded that black holes could be an illusion created by the interaction of particles and gravity. Ultimately, while we are still far from fully understanding what happens inside a black hole, these theories and discoveries offer us a glimpse into one of the universe's most mind-boggling mysteries. A visualization of black holes in 3D would provide a clearer, more vivid understanding of these cosmic phenomena. Until now, we've primarily studied black holes in 2 dimensions, but by modeling them in 3D, we can gain a better perspective on their true nature. Black holes don't just affect the space within their boundaries, but also the surrounding area. This means that it's not just the singularity that holds significance, but the entire region around it, where space and time are distorted. While it may seem confusing, in simpler terms, a black hole doesn't merely influence the matter inside its event horizon, it also shapes the space around it. We've previously discussed the dust particles and gases around black holes, which play a crucial role in this process. These particles, along with the surrounding spacetime, are influenced by the black hole's massive gravitational force, pulling everything toward it. This gravitational pull affects everything within its vicinity, distorting spacetime itself. Rather than focusing on a single point where all matter is concentrated, it's important to consider the possibility of a moving black hole, an entity that consumes more matter and grows increasingly powerful over time. This could even suggest that a black hole might one day pass near Earth, posing a potential threat. Recent advancements in black hole research have brought us closer to understanding these mysterious objects. We now know that inside black holes lies a singularity, a point of infinite density where the laws of physics break down. However, there is still much to learn. The study of black holes could lead to groundbreaking discoveries, possibly revealing new worlds or even other universes we never anticipated. The concept of black holes began with Albert Einstein's groundbreaking theory of general relativity, published in 1915. His equations predicted the existence of objects with such intense gravity that not even light could escape. This led to the idea of singularities, where the curvature of spacetime becomes infinite. While this theory remained dormant for years, the discovery of Cygnus X1 in the late 1960s, an X-ray source orbiting an invisible companion, provided strong evidence for the existence of black holes. Understanding the anatomy of a black hole is crucial. It consists of 3 primary regions: the outer and inner event horizons and the singularity. The event horizon is often referred to as the point of no return, the boundary beyond which nothing can escape the black hole's gravitational pull. Inside the event horizon lies the singularity, where gravity becomes so intense that matter is crushed to infinite density, challenging our current understanding of physics. Black hole research has made significant strides, especially with the development of technology such as the Event Horizon Telescope, EHT. In 2019, the EHT captured the first-ever image of a black hole's shadow, located at the center of the galaxy M87, 55 million light-years from Earth. This image provided experimental proof of many years of theoretical work, revealing a bright ring formed by light bending around the black hole's event horizon. An intriguing aspect of black holes is their potential role as gateways in spacetime. While the singularity remains a mysterious and impenetrable region, some physicists speculate that black holes could connect distant parts of the universe through wormholes, hypothetical shortcuts in spacetime. These Einstein-Rosen bridges could theoretically allow for instant travel between 2 separate points. However, traversing a wormhole would require exotic matter with negative energy density, a substance that hasn't been observed and may violate known physical laws. Another captivating hypothesis suggests that black holes could be interdimensional objects, inspired by the holographic principle in theoretical physics. According to this idea, the information inside a 3-dimensional space could be encoded on a 2-dimensional surface surrounding it. Applied to black holes, this would mean that all the information contained within a black hole might be projected onto its event horizon, challenging traditional views of black holes as purely gravitational entities. Some physicists also propose that black holes could be the source of dark matter, a mysterious substance that makes up a significant portion of the universe's mass. Dark matter doesn't emit, absorb, or reflect light, making it invisible and detectable only through its gravitational effects on visible matter. It is believed that primordial black holes formed in the early universe could account for some of dark matter's gravitational influence. However, this theory remains speculative and requires more observational evidence. The study of black holes extends beyond astronomy, offering profound implications for our understanding of the universe. These cosmic giants influence the formation and evolution of galaxies, as their gravitational pull can disrupt nearby stars and planetary systems. Understanding how black holes behave is crucial for predicting the long-term dynamics of galaxies and the distribution of matter across the universe. In addition to their gravitational effects, black holes are also powerful sources of energy and radiation. As matter spirals into a black hole, it heats up and emits vast amounts of energy across the electromagnetic spectrum, from radio waves to gamma rays. This phenomenon, known as active galactic nuclei (AGN), powers some of the brightest objects in the universe, illuminating the complex interaction between massive black holes and their host galaxies. The discovery of gravitational waves in 2015 provided another revolutionary tool for studying black holes. Gravitational waves, ripples in spacetime caused by catastrophic events like the merger of two black holes, allow scientists to infer properties of the black holes involved, such as their masses, spins, and distances. This observational breakthrough marked the beginning of gravitational wave astronomy, opening a new window into the most extreme phenomena in the universe. Exploring black holes also challenges our understanding of quantum mechanics and the nature of information in the universe. The concept of Hawking radiation, proposed by physicist Stephen Hawking in 1974, suggests that black holes can emit radiation and gradually shrink over time. This idea introduces a paradox. It implies that information about matter falling into a black hole could be lost, violating the fundamental principle of quantum mechanics that information must always be preserved. As our technological capabilities continue to advance, so does our ability to explore the mysteries of black holes. Future missions and observatories, such as the James Webb Space Telescope and the Laser Interferometer Space Antenna, LISA, promise to further enhance our understanding of these enigmatic objects. These missions will examine a wide range of cosmic phenomena, from the formation of the first black holes in the early universe to the dynamics of black hole mergers and their role in shaping galaxy formation. In conclusion, black holes represent one of the most fascinating and significant mysteries of the universe. From their theoretical origins in Einstein's equations to their experimental confirmation through advanced telescopes and gravitational wave detectors, black holes continue to push the boundaries of our understanding of spacetime and the fundamental laws of physics. As we embark on future investigations and discoveries,